Okay. Settle down. Okay. Yeah. So the last talk ran a little long, so I'm not going to make it in the time slot from the as stated on the schedule. We're probably pushing it forward a little. Okay. So. I'm going to be talking about some things about the SFrame and the SGraph, and kind of like what a little of kind of what we do at Dato, and why you should care, I guess. So, what is Dato? So, if you have heard of GraphLab, we were called GraphLab. We changed the name to Dato sometime in the top. I think is getting cut off on this side. Let's do it again. Better. Come back. Okay. Anyway, so it was founded somewhere around mid-2013 by Professor Carlos Gashin. We changed the name to Dato sometime early this year, largely because when we call it GraphLab, everyone thinks we are a graph database. We are not a graph database. We do a lot more. Right, and so who am I? So I was a student of Carlos, so I was one of the co-founders together, plus a few of his students. We started Dato. I did my thesis work on distributed machine learning. At one point, we built this kind of power graph. That's kind of the core bit of my thesis, which is essentially the world's fastest distributed graph processing framework, though it's more like HPC style of distributed processing. So now I'm the co-founder and the chief architect at Dato. Okay, so what is it we do? I will not go too much into the more pitchy stuff, but essentially the basic idea is to make it easy for people to go from all the way from data engineering to making machine learning models, iterating on that, and taking it into production. Is to because essentially we begin where we have a large group of kind of machine learning people. We play with a lot of data. We take in a lot of customers send us data. We have seen data of all types, of a lot of different types. And what we do is we just try to make it really easy for us to manipulate and do stuff with those data, and therefore make it really easy for everyone else to manipulate and do useful stuff with the data. Okay, so let's take a really quick demo. Okay, so what we are is a Python library with a C++ backend. Okay, and you begin essentially import GraphLab SGL. Now, so we are going to take if you guys came to my tutorial, this is kind of a very, very condensed fragment of it. So this is the Yelp review data set. Okay, so each row of this Yelp review data set is essentially a JSON string. Okay, now one way we can think about such a file is that it's actually a CSV file. It's a CSV file with each row is a dictionary. Each row contains exactly one dictionary, and that's all it is, right? So we call read CSV on it with no header. We read the first 100 lines. So with the new Jupyter, I think our incremental printing broke a bit, but we correctly infer that the column type is one dictionary. We parse it, and we get a table. Okay, so we have some most interesting type inference CSV parsing capabilities, right? And each row is essentially exactly one dictionary. You can arbitrarily slice and dice like an array. Now, except that the SFrame actually goes out, actually scales out way beyond memory. Okay, so we have interesting capabilities to unpack columns. For instance, essentially X1 is just this big dictionary, right? So we can unpack the column, and we end up with a table of business ID, date, review ID, stars, and so on. Okay, we can see the votes here, which, there we go. Scrolling is slightly awkward, but votes here is still packed in, still a dictionary, funny, useful, and cool. We can further unpack that. We can unpack on votes again, and then now we pull out just the vote. We pull out we expand out the votes column, right? So we're very nice, very easy unstructured data processing capabilities. Now, something we can do quickly, just to much better than just displaying an IPython notebook, is our show function, which very quickly gets a summary of every column of the data. Right, so all these summaries, these summary views are done by using very fast one-pass sketching procedures. So we can get an estimation of the number of unique items. We get approximate counts of all the frequent items, and the number of stuff we can get. We can get approximate quantiles we can get quantiles on everything. So for instance, date. Very quickly, we see the most frequent item is January 3rd, which is conveniently my birthday. Yep. So, and also very nice is a table view, which I have to zoom out to just give you a sense of it. You can look at all the data very quickly. This is essentially Excel is a very powerful tool. Excel is very, very useful. It just gives you a very quick overview of your data. This view scales regardless of how big your SFrame is, how big your data is. We page in things as you scroll along. Okay, so going back to here, SFrames are column-wise mutable, so you can modify and add or remove columns easily. You can do numeric operations on columns. And each column is really as an S array, so we can quickly create a column called total votes, and we have very powerful filtering capabilities. So, total votes greater than 0. This essentially returns me an S array. Type is integer, but it's binary, ones and zeros for each row, whether the number of total votes is greater than 0. And then we can do this, which is what I call logical filter. So reviews, select all reviews where the number of total votes is greater than 0. Okay, so this is the first hint that the SFrame is doing something interesting in the back end. We do not know the number of rows in this SFrame. So in the back end, a bunch of query optimization is being performed. So say if we want to do some classification of funny, right, whether a review is funny or not. Okay, so let's say that reviews with at least one vote for funny is funny, right? And this will just binarize the funny column. We select out just the text and funny, so we are just going to look at text, the text column. And we can do count words, so we'll just do a sparse model, just a parameter for each word. Okay, so that just takes each column and turns it into the text column and turns it into a dictionary, right? So you see a lot of things that all run instantly. There's kind of the lazy evaluation capability going in the background, which I'll talk about. So now I'm going to go quickly build a logistic regression classifier on reviews, categorizing on funny. It will take all the remaining columns, which in the case is just text, and it will try to do something sane with it. You automatically take a dictionary column, interpret a sparse feature. If you have a string column, you automatically interpret a sparse feature. It is a little longer, largely because of lazy evaluation going on. It has to evaluate everything above, and also incremental printing is broken, which we will have to fix. It will take approximately 20 seconds. So it automatically picks a solver for you. We have about 3 solvers in backend, and we end up with a model which we can then use and take to production using some of our remaining capabilities, which I will not demonstrate here. So that's it. Ooh. That's a quick demo. Okay, so first, yes, we run on a single machine. This is right now all running from my laptop, and when you have a bit, yeah, and everything is being done on one machine. So here's the question: what can you do on a single machine? How much can you do on a single machine, right? And this is what we can do on a single machine. We build a collaborative filtering model, matrix factorization, on about 20 billion user item ratings. We can perform page rank on 128 billion SGraph, right, and on a single machine. How? And this is kind of the 2 core data structures we have, which is the SFrame and the SGraph. So the SFrame behaves a lot like it essentially behaves a lot like a Pandas data frame. It's easy to make S-frames. You construct it from so from here I'm just constructing from a dictionary with one column X and 5 values. We can do modification, arbitrary modification of columns. So it's not quite. It's not quite like a database table, right? You can perform a degree of mutation on it. It's column-wise immutable, though. So we can apply arbitrary Python lambda operations. We can create new columns very easily using vectorized operators. And we can very easily subset like columns, right? And the design principles we go in the back end is to have a kind of graceful degradation, which is we have an objective, which is we try to always work. Regardless of how much memory you have, we try to always work. We have very rich data types. As we see, we have a list, we have a built-in recursive list type, recursive dictionary types, which those can recurse arbitrarily, and with very powerful operators to unpack, pack them, stack them in different ways. We also have an image type, which is very useful. We pack an entire image into one cell, so each row is one image. And the backend is a columnar architecture to support very easy feature engineering, addition and removal of columns, and so on and so forth. And the key is really columns are first-class citizens. We have a type called an S array. So the S-frame really behaves a lot more like an arbitrary collection of columns than a database table. So the internal representation of the S-frame is actually, it turns out, not very complicated. So say we are creating, we load an S-frame from disk, right? So when loading S-frame from disk, because the backend of the S-frame is based on disk-based storage, we cache a lot in memory, but it's based on disk-based storage. So opening an arbitrary large S-frame just revolves as pointing to the file. We do not actually need to load anything. So what that does is we're creating an S-frame, 3 columns, and those just point to their corresponding locations on disk. Say we load a different S-frame, right? So maybe someone else has a normalized rating field, for instance, right? And that just creates a new S-frame which points with the same 3 columns pointing at different locations on disk. We create a new we add a column to our first S-frame called maybe a normalized rating, and all that does is create a new column and points it to the column in the other file. We compare a difference between the rating fields of these 2 columns. That creates a new anonymous column, right? Which is generated by computing the difference between the rating field in one and the rating field in the other. And well, we call it diff. This is an S array. And this is our equivalent of an external memory NumPy array. And if we add this column to our S-frame, assigning the name diff, that just creates a new entry in our S-frame SF called diff, which points to our new anonymous S array. The internal physical representation is a column store. Kind of a user, so for instance, I have 3 columns, user, movie, and rating. It's a column store, kind of arbitrary kind of misaligned blocks. Essentially, this allows us to get the maximum amount of compression regardless of how large, for the maximum amount of compression for each column, regardless of how large the data is. So because if we stick an entire image in a cell, for instance, right, then if there's only that much, and you have very sparse, small numeric values everywhere else, you don't want to align the table against that very big image value, right? So this allows us to compress user, movie, and ratings in every column using the best compression procedures possible for each one, right? And all these are packed together into a single file, or potentially multiple files in arbitrary order. And we have a series of compression algorithms going on in the back end to make it go fast. So then, how do we perform evaluation on this thing, right? Where are all these math operators? How do we do projects and joins and so on? So this is where kind of the idea of lazy evaluation comes in. So lazy evaluation is very common. So Spark has it, Blaze does that to some, and it essentially lets us pipeline operators. And this is especially important if we are going to external memory, going to disk, going to SSD, because this avoids us writing out to disk all the time, right? And but because our columns are first-class citizens, this requires us to extend somewhat from classical SQL optimization procedures, because we need to maintain both tables and columns. And the mechanism of doing so, we can give a quick example here. So this, we learn an SFrame from some source. We're going to project out the ratings column. So ratings is an S array, and what that does is just creates a new node in the graph. We multiply by 2, creates a new node in the graph, and ratings now point to the new node. We assign it back to the original SFrame. So we call it union columns, but essentially we're taking columns from 2 different places and combining them together. And we do a sum on that, right? So once again, we project out the ratings column, and then we perform a reduction on that, right? So now, next is kind of the idea of query optimization. Given this graph, how do we best perform the reduction operation? First is that we can say a project can be fused into a union. We do not need to union to project out one column. We can pass the project through the union. And because we can read a single S array directly, we can combine the projection into the source itself, right? And so this is the actual physical plan that's being executed when you perform that sum. So we take the original source, we multiply it by 2, and perform reduction on it. So the idea of query optimization gives you this very, very rich source of performance optimizations, pushing filter operations upwards, pushing project operations upwards, pushing complex join operations downwards, not downloads, join ordering, and so on. We have only a few implemented now in GraphLab Create 1.4. Which is hopefully coming out in about a week or so. In the last month or so, we completely re-architected the backend execution engine of the SFrame. So you actually see some good performance gains with the new 1.4 engine, and it gives us room to start throwing together all these query optimization tricks. So here is a really cute example. Left side is it's kind of like a fast testing thing. Left side is a randomly generated plan. The right side is the actual optimized plan. And this is just kind of a cute example of query optimization being performed. In this case, we are kind of fast testing our query optimizer. We generate a random plan, we execute it, we optimize it, execute it again, we see whether we get exactly the same answers at the end. Okay, but even the performing execution requires a lot of care when it comes to optimization, especially when you are performing a lot of compression, right? Because you come at the risk that when you uncompress the data, it will no longer fit in memory, right? Because, for instance, our block sizes are something like 64 kilobytes. We pass through 2 phases of just regular, kind of like regular integer encoding followed by LZ4 encoding. So what happens if your numbers are all zeros and ones, and is an integer column, right? Now, first, all that just get packed into 1 bit per value, and then after that, LZ4 may take it even smaller. And our target is 64 kilobytes compressed, right? So when uncompressed, that single cell can become a million, a single original 64-bit can become a million integers, can become 10 million integers. So you have to be very careful when performing decompression. So we have a lot of optimization in the backend. So we have a coroutine-based incremental decoder. So we decode on the fly. We do not ever need to maintain all the decompressed information in memory at any one point. We only need to hold compressed state in memory, runtime input skipping, and so on and so forth. Right, and the outcome is that just looking at filter performance, and as it turns out, also group by performance, but I don't have the benchmarks here, we can outperform many other things on a single machine. So this is just a simple filter operation. We're selecting, it's fully synthetic data, really. This is some on the Spark benchmarks page, where we ran, just select pages where some page rank value is greater than 100. We can run it faster on a single machine than anything else on 5 machines, or even when the selection output is bigger. And how large does this scale? We cache significantly memory. We go out to disk. The largest synthetic set we have performed has 950 columns and 1 billion rows, dense numeric, or about 1 trillion numeric set values. And all that fits on a single machine, and we can do useful things on it. There's no real limit on the number of rows, but there's practically, usefully about 100 to 1,000 of columns. There's the limitations of most columnar representations, and something we are optimizing. Though that said, we had a customer use us on about 100,000 columns, and I'm surprised it works, but it does work. Yeah, but you start as the number of columns start to increase to tens of thousands. Wide reads become slower, and that's kind of a necessary effect of most columnar databases. So, how do we get graphs from this? So this is so we have been known for graphs. Our original research group was known for graphs, very big distributed graphs. We also had this project called GraphQi, which looked at external memory graphs, doing computation on external memory graphs. And so we want graphs. And people find graphs useful. People have social networks. You have user item graphs and things like that, right? So our SGraph is our counterpart to the SFrame table, but handles graphs, and internally is built entirely using SFrames. So we shard the vertices. Essentially, really, we randomly partition the vertices into a collection of shards. You can set the number of shards, and each shard is an SFrame, so you can have arbitrary attributes on vertices. Essentially, you can go sgraph.vertices, and you get an SFrame, which you can then join and do arbitrary operations with any other table. The edges, however, are partitioned into p-squared partitions, p-squared S-frames, right? Where, say, partition 2,4 contains only edges connecting vertices in partition 2 and vertices in partition 4. And because they're S-frames as well, you can now store arbitrary, it's still a table, you can store arbitrary attributes. You go sgraph.edges, you really get an S-frame back. And you can do whatever you want with it, right? So, and to perform computation, so this also lets us do extensive compression, because we need less bits to represent source IDs and destination IDs and so on. So compression turns out to be much improved. So so to perform computation efficiently without extensive paging, we walk the graph essentially in the Hilbert curve ordering. So we sweep through the edges in the Hilbert curve ordering, and this gives us good performance gains when accessing vertex data. Right, and really, all you need for a lot of graph computation operations is the ability to sweep through edges very quickly, as fast as you can, right? And the outcome is that on a single machine, we can outperform 16 machines. And this is on the Twitter graph, PageRank. And connected components, we significantly outperform 16 machines. And this is because there is a really nice connected components algorithm that is really, really, really hard to distribute. Union find. The union find algorithm can get you all the connected components in one pass, but then that algorithm is extremely non-trivial to distribute. And so for all the other distributed graph procedures, they kind of do by propagation. They require a number of essentially up to diameter number of iterations to converge, whereas we can actually complete it in one pass efficiently in shared memory with one machine. So scalability of this thing. So this is something new in 1.4, which once again will come out in 1 week. We managed to run this on the largest public graph you can find, called a common crawl graph with 3.5 billion vertices and 128 billion edges. Represented naively on a single machine requires at least 2 terabytes of memory, right? Kind of 2 integers per edge. With some care, you can get less, but then you pay in different ways, right? And we run this on one machine, one SSD, PageRank at 9 minutes per iteration. We run full connect components in about an hour. So we have these two core underlying data structures, SFrame and SGraph. But our key object, these two data structures, SFrame and SGraph, will be open source. They are technically open source, but it's not exactly a Python package right now. But you will soon. I'm trying to refactor the code in a way so that we can compile these into a separate Python package. These two pieces will be open source, and you will be able to use them anywhere. So the key, however, is everything else in the pipeline as well. How do you get machine learning? How do you get deployment? I will not be talking about deployment. Rajat talked about deployment extensively yesterday, but machine learning then, right? So all our machine learning algorithms use SFrame as the backend data source. But the model itself must be in memory, but the implementations itself are in C++ and use whatever it takes to go fast, essentially. Parallel execution, control memory access races. This is algorithms are some machine algorithms are actually robust to this if you are careful. There are proofs about that. Multiple solvers for different regimes, GPUs, And one of the key is that robustness and ease of use is the key objective, not just performance. The idea, we work effectively with both sparse and dense regimes. We have multiple solvers, optimizations for both sparse and dense regimes, and we probably have one of the most robust linear solvers out there that work across all regimes effectively, whether you have a ill condition columns and so on. We detect it and we try to correct for it. And our VP of engineering said garbage in, guidance out. This is kind of the objective for the machine learning algorithms. This is a really tall order for many machine algorithms. It's not something which research has done very well at, to get garbage and guidance out. But and that's when that amount of diagnosis we can do on the data in reasonable time. But this is something we do try hard to achieve. And we have a large collection of machine learning models. Linear models, trees. We have a really, really good collection of recommended algorithms, deep learning with GPU capabilities, clustering, text models, and so on. Right? Should go to the webpage and look at the list. And the performance is quite good. We outperform about 5 nodes on MLlib, and we did, I don't have the numbers here, we have a chart elsewhere, but we pretty much get better results than, higher accuracy than MLlib on all data sets, right? That's the question of robustness, which is something that we take a lot of care to ensure. So we can get logistic regression on the common 100 gigabyte data sets on commodity hardware in about 1.5 hours on one single machine. And similarly, collaborative filtering models, about 4 billion user item ratings in about an hour, and this scales to about 20 billion. So essentially, here's the question. So it's time to rethink the idea of big data. How big is big data, right? So how much can we do effectively on a single machine? And a single machine is much cheaper, easier to maintain, and much faster to get working, right? And it can scale to much, much bigger data sets than you think, with the appropriate thought going into data structure design and so on. Right, so this is the last bit. So distributed. Why distributed? Distributed is something we are looking into. And there are good reasons to distribute. So when you have IO-bound tasks, when going distributed, you get n times the number of disk, network, memory bandwidth, or you have compute-bound, embarrassing parallel tasks. And so these are things we are working on. SFrames are good at distribute is essentially very similar to a database like distributed OLAP database like ideas, and we're working on it. Graphs, much harder to distribute, but I have done it many times now. I spent 4 or 5 years of my PhD time working on distributed machine learning, and I do not recommend wasting time on this. But still, we have worked along graphs, and this is something that we have very, very good ideas on how to do well. But distributed machine learning. So There's been many claims of distributed machine learning, but here is a common performance fallacy. So say I come up with a distributed algorithm for machine learning model X. Pick your X, be it neural networks, or be it collaborative filtering, or something else. And we get this speed ups. So on one machine, we see 1,000 examples per second. On 60 machine, we can go through 15,000 examples per second. 64, we can go through 62,000 examples per second. Okay, that's relatively linear speed up. So have we solved the distributed machine learning problem for model X? So here are the same things kind of put together in comparison. We have two algorithms. Algorithm A, we run on a single machine. We get very high convergence rates. We only require 10 passes through the data. We have algorithm B, it's easier to distribute. It has low convergence rates, requires about 100 passes through the data, but each pass is very fast. So which is faster? It kind of depends a lot on system and network characteristics. If you have less than some X number of machines, A is faster. Otherwise, B is faster for unknown X. The key to looking at distributed speedups is we should be comparing convergence rates, not throughput. Convergence rates against the best known single machine algorithm, right? And here's a good example. So this is a chart from a recent paper from Google looking at distributed deep learning. Okay, so this is from co-authored with Jeff Dean, so we can be sure the system is really, really solid. This is we're looking at convergence rate time to 16% accuracy. Now, if you look at this carefully, the dot on the left is GPU time. The dot at the bottom there is their SGD time. Yeah, it runs much faster, but it took 600 machines to decrease training time by 3 times. Right, so distributed deep learning is kind of something we can tell, there's still some ways to go, right? When the single machine, essentially, if I were to just pay a little bit longer, 3 times the runtime, I can get pretty much as good. Not many people have 600 machines lying around, right? So distributed ML, interesting machine learning is notoriously hard to distribute effectively. There are some special cases people have worked on, included kind of like, so there are some thoughts we're kind of like going beyond MapReduce to think a bit kind of more of a HPC style, and to distribute only when it makes sense, balancing convergence rates and throughput, and this is something we're working on. Thank you.